These are the notes for section 3.2 and 3.3. And the first thing we're going to talk about here is what's called the ruler postulate. And so the ruler postulate, it's basically saying this: the points on a line can be numbered which makes you think about a ruler, kind of a scale, can be numbered so that positive number differences, that is when you subtract two of the numbers that refer to the points on the line, so positive number differences measure distances. Now, because you're measuring distances, it's important that you are talking about positive differences. You wouldn't want to take two numbers and subtract them and come up with a negative. You couldn't call that a distance. So let's look at what that looks like with a ruler. So here's a line, and I've put a ruler up next to it. Let's say that I have a point on the line A, and A's coordinate is here associated with 1 on the ruler. And let's say B is right here, maybe at 3, and its coordinate is 3, but we could also just call it little b. And let's say C is on 4. Okay, so no matter what point I choose on here, I can choose any point I want. I can choose this point right here, and I can find a coordinate that's associated with it. Okay, that would be 2 1/4. It doesn't matter which point I choose. I can always put a scale on a line so that the numbers can be coordinated with that scale. Now what it's saying is positive number differences would represent distances. So if I wanted to find the distance between A and B, I would just take the difference between those. For these, that means taking 3 minus 1, and that tells me that the distance between these 2 points is 2. If I do these two, I would do 4 minus 3, and knowing then the distance there is 1. Basically, you're just looking at what is the difference between the coordinates. In this case, it's a distance difference between B and A. In this one, it's C and B. And you'd want to make sure you subtracted the smaller one from the bigger one. The next thing in this section is a definition. It's the definition for the betweenness of points. And that definition says that a point is between two other points on the same line if and only if its coordinate which is the number that it's associated with, is between their coordinates. Now, the notation that we use for that is A-B-C, but we read that as B is between A and C, if and only if, that's our definition, remember, the coordinate for A is smaller than the coordinate for B, which is smaller than the coordinate for C, or vice versa. A is greater than B is greater than C. The key being that B is between A and C if and only if its coordinate is between their coordinate. It's stuck in the middle. So let's look at the ruler again. For our picture here, obviously B is between A and C because the coordinate associated with A is 1. The coordinate associated with C is 4, and 3 is between 1 and 4. The last thing in section 3.2 is a theorem. So we had a postulate, which had to do with measuring distances between points. The definition, which had to do with when is something between two points, and then, or when it's a point between two others. And then the theorem for the betweenness of points is this: if we know that B is between A and C, then if we take the length of AB, so the distance between those two, plus the length of BC, so the distance between those two, then what we should get is the total distance AC. That will only be true if B is between A and C. So let's look one more time at the number line. So the idea of the betweenness of points theorem is saying that we know B, if B is between A and C, then we can be guaranteed that the distance between A and B, which we know is 2, plus the distance between B and C, which we know is 1 based on our coordinates, should equal the distance between A and C, which in this case is 3. We know 2 plus 1 does equal 3, so it makes sense. And we only are guaranteed that if B is between A and C on the line. If B was someplace else, like let's say out here somewhere, then the distance between A and B plus the distance between B and C would not equal the distance between A and C. In the next section, we end up looking at similar things to what we had in 3.2, but they have to do with angle measures and protractors as opposed to lengths and rulers. So first of all, we start off with a postulate, the protractor postulate, which says the rays in a half rotation, so that means you have to be within 180 degrees, not any more than 180 degrees, or you go more than half of a rotation. So the rays in a half rotation can be numbered, just like we said the points on a line can be numbered for the ruler postulate. Well, the protractor one says the rays can be numbered from 0 to 180, so that positive, this should sound familiar to the ruler postulate, number differences now before on the ruler postulate it gave distances. In this case, since we're talking about rays and measuring the difference between their positions in a half plane, then the positive number differences measure angles. So let's look at what that looks like on a protractor. So here are two rays, and I set a protractor up on top of them, and you can see this first one is measuring at 40 degrees if I'm using this outer scale. And it doesn't matter, I could use the inner one too, but I'll use the outer one for here. So this one's 40, so that's the coordinate associated with it, and have to use the same scale. This one's associated with 110 for the outer scale. And so if I want to know what the angle is that they're measured, I could have set my protractor up so that one of them was on 0, but it really doesn't matter. All I need to do is look at the distance, or the difference between those two. So 110 minus 40 tells me that this is a 70-degree angle. It doesn't matter whether I even know what those numbers are. I could call this A and this B, and then A minus B or B minus A, whichever one's positive, would tell me the measure of the angle. The next thing in this section has to do with just some definitions of kinds of angles. I'm sure that you've seen this before. An angle is acute if and only if it is less than 90 degrees. So we could say the angle measure A is less than 90 degrees. It's right if and only if it is, if and only if it is equal to 90 degrees. So your angle measure is 90 degrees. It's obtuse if it is more than 90 but less than 180. So to write that as an inequality, your angle measure is between 90 and 180 degrees. That makes it an obtuse angle, and it's a straight angle if and only if it is 180 degrees. So its angle measure is 180 exactly. We call that a straight angle. The next thing in this section is the definition for betweenness of rays. So we have the betweenness of points theorem, which we thought about. Remember, the coordinate of the point had to be between the other two coordinates in order to be considered to be between the 2 points. Well, the same idea is going to be true for rays. So a ray is between 2 others in the same half rotation if and only if its coordinate is between their coordinates. So in symbols, we say this: ray OB is between ray OA and ray OC if and only if the coordinate associated with ray OA, which we'll call A, is smaller than the coordinate associated with ray OB is smaller than the coordinate associated with ray OC, or, again, the other way around, A is bigger than B is bigger than C. Let's look at that on the protractor. So we have ray OB being between ray OA and OC as long as its coordinate, which in this case is 60, is between the coordinates of the other 2 rays. And in this case it is. 60 is between 40 and 110. Even if I use the other numbers associated with this, if I use the 140, the 120, and the 70, you can see that the 120 is still between 140 and 70. Now, one thing you have to be careful of with this is if I was to draw my ray so it was going out here, that ray would not be considered between these 2 rays because it's not in the same half plane. In order to be between, you have to be in the 180 degree or less space. Okay? That's for betweenness. So then the last thing we have here is the betweenness of rays theorem. Well, the betweenness of rays definition had to do with the coordinates of the rays, just like the betweenness of points definition. The betweenness of rays theorem has to do with their angle measures adding up to the whole part. So it says if OB is between OA and OC, then the measure of angle, I'm going to start this down lower here, then the measure of angle AOB plus the measure of angle BOC is equal to the measure of angle AOC. So let's look at what that has to do with our protractor. So our theorem says as long as OB is between OA and OC, then the measure of angle AOB, which in this case is 20 degrees, plus the measure of angle BOC, which is 50 degrees, is going to equal the measure of angle AOC, which we had already established was 70 degrees. That's not going to work if we have that angle, or that ray that's out here. If you look at that and you say, well, the measure of this angle plus the measure of this angle, if this was B out here, then AOB would be this, and BOC, well, technically would be this. It's definitely not equal to that when you add those together. So it only works when B is between, ray OB is between ray OA and ray OC. The final part of the notes is a proof for the betweenness of rays theorem, but we're going to do that in class. So for right now, you can just leave that blank. And we're done.